Testing. Hello, everyone. Welcome to the workshop on the post-construction requirements and Santa Barbara County Stormwater Technical Guide. My name is Kathleen Garnand. I'm a civil engineering associate with the Public Works Department at the County of Santa Barbara. And this is the third workshop that, that we've held under this Prop 84 grant. It'll be the last of these workshops. And this one obviously is being taped and will be available for your colleagues. So if you want to let folks know if they're interested in getting this information, that this will be available for them on the Project Clean Water website. That's SB Project Clean Water. And one of our prior workshops a year ago was also taped. We went in, Dan Cloak also presented that. We went into a lot more detail on LID design. So if you would like to get a little bit more and a little bit deeper into this, you can also listen to that particular workshop. With me today and doing this presentation is Dan Cloak. Dan Cloak, Environmental. He wrote the Stormwater Technical Guide along with the partner cities in Santa Barbara County. The guide is it gives guidance on implementing the post-construction requirements. So it's usable by any municipality and any developer on the Central Coast trying to implement the post-construction requirements. It's not unique to Santa Barbara County. And Tony Dubin, who's worked with Dan Cloak for many years. Tony is the master craftsman of the Excel spreadsheet, so the stormwater calculator. And Tony will go over the use of that calculator and how it complements following the technical guide. And I'll go ahead and hand it over to you, Dan, and you can decide how you want to talk to the audience.
Okay. All right. I'm gonna kind of stroll around just because I'm most comfortable doing that, and I'm going to jump right into the presentation because we've got a lot of information to present, and you know, it always seems like we've got plenty of time, but noon rolls around pretty quickly, and we find that we want to make sure that we get all the information out to you. So let's go ahead and get started here with what's new. How many folks have used the Stormwater Technical Guide before or familiar with it? So we have maybe 2/3 here of the folks how many folks have used the calculator? Okay, and how many have attended the previous training? Here. Okay, all right, so about half, maybe a little more. All right, well, with that knowledge, let's move ahead into what's new and go to the slides. So let's start with what's the same, what's not new. The first of those is the emphasis on low impact development. So definitely that continues to be the focus of the guide's method of implementing the post-construction requirements, basically dispersal, bioretention as being the principal strategies for managing runoff. With that is the key requirement that in order to do an LID design, and particularly in order to check an LID design and ensure that it complies with the PCRs, it's necessary to delineate drainage management areas. So we continue our focus on that as being the sort of the main aspect, the first thing that I advise municipal reviewers to take a look at when they first open up a submittal is, do they have a diagram of the site showing the entire site divided into distinct drainage management areas, so we can then follow where the runoff from each is going. And then, you know, in order to make the whole submittal process work smoothly, we emphasize that applicants should use the guide. We have even more emphasis on using the calculator. In the current version, there's kind of an option that say, oh, well, if you're a tier 2 treatment only project, you know, you can submit it, you know, just using your own Excel tables or whatever. The calculator's pretty much been proven. I've never heard anybody say that it's hard to use or confusing in any way. So we're pretty much going to even more emphasis saying this is the method by which you submit your calculations. Use the calculator for tiers 2 and 3. And then we have templates. Of course, people can, you know, always do their own thing, but they're there. They're the Word documents. they're meant to organize things into a consistent way of looking at it, again, to smooth the process and to smooth the conversation that needs to happen between the applicant and the reviewer. The technical stuff that's new are really two things. One is we've found a way to reduce the storage volume, the amount of gravel that's required beneath the underdrain on bioretention facilities. And this is done by incorporating an orifice on the underdrain, which then during peak events, during events which are on the large end of the spectrum of storms that we need to control, will allow runoff to back up and make use of the storage volume in the pores of the soil mix, and even more importantly in the reservoir on the surface of the bioretention facility, so we can get some credit for that. By getting credit for that storage, we can then reduce the storage underneath. I think it's a pretty good move. And so this shows that is we also made it so you can now specify a deeper reservoir in order to take advantage of that volume. There's no real advantage in doing that before, but now that we're taking advantage of the surface volume, if you had a larger bioretention facility, say the size of this room, you might find that you wanted to make a gentle slope coming from the edge down to the bottom. By the time you got to the center, you might be 2.5 feet deep. And then you would have it, if you could go for an average depth up to 18 inches, you can specify it either as a depth or a volume and take credit for that because of the effect of being able to back up to it, into it during the big storms. So we hope this will help ease the problem of having to dig excavations so deep or to use so much site area in order to comply with PCRs using bioretention. The orifice design on this, generally the parameters are that the overflow structure needs to be something that's like pretty solid and permanent. Concrete catch basin is generally what we're looking for, so that the underdrain pipe can then penetrate either by ordering it that way, precast, or by coring it. Putting the underdrain through the wall of the catch basin that's used as an overflow structure. And then the construction beyond that is pretty simple. That end of that pipe's threaded, and the cap is put on that pipe, and then the cap is drilled. Here's one that is currently in operation in Contra Costa. And as you can see, those orifices get really small because you really need to provide that backup. We have not seen any problems with clogging. That's typically expressed as a concern. Won't something like that clog? Answer is as well, this is only passing water that has been filtered through the sand compost mix. And so it's somewhat unlikely that particles will get in there. The pinhole there is not at the bottom of the flow line. It's raised a little bit, so even if you get some sediment settled down in your pipe, it isn't necessarily going to block that orifice. If it did, it's a good idea to be able to have access from inside that catch basin structure, and then it's just a simple matter to unscrew the cap, flush it out from the inside, screw the cap back on. So again, it's an option. People don't have to do it, but there is an advantage. You get about 20% reduction in the volume requirement, and so we wanted to make that available if applicants wanted to go in this direction. Another thing that we realized after we got started with implementation is a lot of the time a flood control basin is required anyway. It's a separate set of requirements. And we get the question, well, gee, this is kind of crazy. We got two things to handle runoff. How come we're having to follow one set of requirements and build a structure to meet the MPDS requirements and then a whole nother one, and can't we get some credit here back and forth? So really this can be done even with the current calculator, but we wanted to make the instructions for doing so very explicit. And the basic way this works is that when you plug your area into the calculator of your particular facility, and Tony will be demonstrating this in detail later, you can combine the area of the interface between where infiltration can occur, both for the bioretention facility and for the downstream detention basin if you're able to build them in this configuration. So you plug in that as the area, you cut back a volume, and then that volume can be met by any combination of the pores in the gravel layer underneath the bioretention facility and dead storage in the detention, in the infiltration basin, detention/infiltration basin downstream. Now the key to remember there is where you can see the denotation V2 there, that needs to be dead storage. So that is above any release point, any discharge point on that basin. Now, note that the flood control folks are only going to give you credit for the volume above that point. All right, so essentially what this sets you up to do is to build a downstream basin to hold and infiltrate runoff to meet the MPDS requirements, to meet the PCRs. And then on top of that, you're providing the storage that would be required for flood control. I think this ends up being a much more efficient way than requiring the two things separately. I think it'll be a benefit to applicants. And it's a pretty straightforward way. We've tried to explain it as clearly as possible in the new version of the technical guide in order to do that. Any questions on either of these? I think that these are two fairly straightforward changes. I think they're for, depending on what project you have, for certain projects there will be a substantial benefit. In terms of guidance and the available things that we have to help folks along, there's a template for a stormwater facilities operation and maintenance plan. All these items should be up on the Project Clean Water website in about 2 weeks. And then we have some example submittals. And this goes with our idea of basically having multiple ways to learn and understand and check your understanding of what we're asking to be done in the guide. So basically we have the guide, and then we have, the guide includes a checklist if people want to use that. And then we have templates if they want to follow a template. And now we will also have examples of kind of, made up but realistic projects. I took actual designs that I had reviewed on behalf of municipalities and then applied the PCRs as they exist down here to those projects, came up with designs, came up with calculations, and so we'll show them in the calculator. And those are a stormwater control plan for a commercial project, another one for a residential subdivision. When Tony does his presentation, he'll be using the residential subdivision as an example to show you on the screen how the calculator is used. Yeah?
Are you going to have any submittal examples for linear projects? I mostly work with roadway.
Oh.
We can fly into a narrow location.
That's a really good question, and I will say my experience with linear projects is everyone is kind of a different animal, so it's really hard to come up with a generic example that is very helpful. But we should talk about that and try to figure out what are the typical problems and how can we help people move ahead with a solution. Often, well, let's talk about it a little bit in the break, and then maybe at the end we'll have time to have a little bit of discussion about it, because the way the PCRs are written, it does come up, it is a problem, and we need municipalities to have a good strategy for dealing with it. Okay, so how many folks feel like they're really familiar with the post-construction requirements? They know, okay, all right, well, okay, great, all right. So I'm going to give a little bit of background here, beginning with some history, and then getting into a quick summary of which projects apply and what is required. So, as folks may know, really, and this explains one of the reasons why the whole stormwater MPDS thing, not just in Region 3, but everywhere, is kind of messed up, is that all this came from a decision by Congress back in 1987 to amend the Clean Water Act. It was actually the last time it was updated because of the divisions in Washington. There's still not really any prospect of renewing the Clean Water Act even now. And in 1987, they decided to add storm drains, municipal storm drains, to the existing NPDES program, which covered municipal sewage discharges and industrial discharges. And so they put stormwater into a program that, you know, is characterized by systems which are much more manageable, you know, much more predictable in their discharge, much more controlled than stormwater, where basically they're open. You can't control who puts what where. And so that's really why we're sort of dealing with things like numeric requirements now, that it's very difficult to figure out what anybody was thinking when they imposed that on storm drain pipes. The regulations to implement that change to the Clean Water Act were put in during the 1990s. It took until the end of that decade for US EPA to issue regulations affecting Phase 2 municipalities, which are the subject of the PCRs. During the early 2000s, two things happened. One is the State Water Resources Control Board more or less came out with a decision confirming, yes, municipalities have to require developers and development proposals to treat stormwater before it goes off-site, and they applied specific numeric requirements to the design of facilities to accomplish that treatment. We also had the onset of hydrograph modification management and this idea that the NPDES program was not only going to cover pollutants, but it was going to cover the impacts of flows, of increased flows coming off of urbanized areas on streams. And then in 2003, California issued the first Phase 2 permit. It included development requirements, but they were frankly a little vague. You had to have a program. If folks were around working at that time, you had to have a program to address impacts from new development, but it didn't really include a specific requirement that every development project had to be reviewed for compliance. That came into effect with a renewed Phase 2 permit in 2013 statewide. And so if you go outside of Region 3, that is the governing permit. It's provision E12. Frankly, it's a lot easier to comply with. I will say that guiding municipalities elsewhere, Phase 2 municipalities elsewhere in California to comply with stormwater NPDES requirements is very much the same as here, and the big difference is when you get into the calculations and you size the facilities, because we're still doing bioretention, we're still doing LID, but we managed to get into provision E12, basically a 4% sizing factor and 12 inches of gravel on the bottom. So you can imagine that's pretty simple, that's pretty straightforward. We'll see, it'll last at least until they renew that permit. I don't know whether it'll get better or worse or stay the same. I hope it stays the same. But here we have to deal with much larger sizing factors. And just as a rule of thumb, you know, when I do all my design work and explanation of how you translate this into a good urban design, 4% is my reference point because it works really well. Here, it's more like 7-8%, and it's a lot harder to do. And even at 7 and 8%, you still end up with the problems of having to have pretty deep excavations in order to provide the required amount of storage. To implement the PCRs, Kathleen actually got a grant from the State Water Resources Control Board to assist with implementation. We managed to get the Stormwater Technical Guide done a year ago, last February. It says revised November 2015. I'm not going to get it done before Thanksgiving. It'll be out in early December. Again, basically the idea of the guide is really beginning from this point that PCRs are painful to implement, but we don't have to make them more painful for applicants by adding on the uncertainty of how long of what they're actually going to be required to do, how long it's going to take to review, how many iterations. We want to get away, and I've certainly seen this happen when these programs get started or ramp up, is the applicants say, I don't know what the reviewer is going to want. I'm just going to put something together and put it in, and then we'll have them review it and see what their comments are, and then we'll address the comments. And this results in delays, poor designs, confusion, angst, and we would like to get away from that as much as possible and ideally get towards the point where a developer has a very clear idea of what needs to be in their submittal and what they need to show that they accomplished, and that the reviewer has the confidence of knowing, okay, these are the things that I have to check for, this is what I have to check off, and once I've done that, I can have a lot of confidence that I have ensured that my agency is in compliance with the PCRs for this project. So the thresholds and requirements, I tried to boil down the entire confusing pages and pages on this into one simple table with a few lines on it. But basically, if you're above 2,500 square feet of impervious area created or replaced on a project, you have this simple, straightforward requirement to minimize runoff. All you have to demonstrate is that you have at least one feature or device that reduces the amount of runoff going into the storm drain. We have a template to fill out for that. I haven't heard any feedback that there's anything difficult or confusing about that. It just requires basically the same kind of sketch that you might use to show that you were meeting a setback requirement, and some information to fill out. Once you get up to tier 2, above 5,000 square feet, and I'll explain that net word there, the requirement is to treat runoff. Basically, that means, in the way that we are interpreting it, the way the Water Board wants to see us interpret it, that means bioretention. And you could use the 4% sizing factor unless you are in tier 3, going up to the 15,000 square foot requirement, which is, of course, most projects, and I think the majority of projects we're dealing with are probably in tier 3. And that requires the retention of the 95th percentile storm. And that's the piece that makes all this difficult. And then in tier 4, the half-acre impervious area, new or replaced impervious area threshold, there's a requirement to control peak runoff. When the PCRs were negotiated, that was pretty much made to dovetail with existing flood control requirements for peak flow releases. So pretty much it's something that we don't need to address in detail because the flood control districts are already covering it. This net idea, I'm not sure how often, actually folks can tell me whether they've seen this come up, but if you had a 10,000 square foot lot with, that was already paved, and you had a project that proposed to end up with only 7,000 feet of that covered by impervious surface, and they were going to green 3,000 square feet of it. The way that the calculation is presented in the PCRs, and this might be a benefit to some applicants, is not only do you have to address, not have to address that 3,000, but you can actually credit the 3,000 against the 7,000 and subtract it out. And so that means that in this particular case, you would end up with a net imperviousness of 4,000 square feet, which would put you below the threshold, which would mean that you would be in tier 1 and only have to, fill out the form. So just remember that. I'm not sure how often it's going to come up or has come up, but a useful thing for some applicants. So some things on applying the thresholds. Repaving or re-roofing, does it count? Generally, re-roofing, just about never. Repaving, generally not, if the same hydraulic line and grade is kept. Where this gets a little bit complicated is if you were taking a graveled or dirt surface, including, unfortunately, roadway shoulders, and are paving those with an impervious surface. Now that counts towards the PCR thresholds. Does pervious pavement count? And I like to answer this, no. We're counting impervious surface, and pervious pavement by definition is pervious. Where it gets a little dicey is if you have an applicant that comes in and they say, I'm going to get before that 15,000 square foot threshold, I'm going to have 14,999 square feet of impervious surface and a couple thousand square feet of pervious pavement, which I am substituting here for what would have been impervious. And then the question is, okay, where is that and what does it look like? And if that pervious pavement is going to be up on a hillside at an 8% slope, That's like, you really don't want to let them do that. It's just going to slide down the hill. It's, not going to be necessarily very, very effective or very useful unless they spend an inordinate amount doing trenches and other things in order to hold that runoff in place. So that's just the thing to watch out for. If it is on a flat site and there is competent soils with good drainage, go for it. I don't think the Water Board has any problem with that. It's one of the things that's kind of intended is to encourage the use of pervious pavement. So if you can get below the threshold by using pervious pavement in a responsible, useful way, then do it. It should meet the specific criteria that we have in the guidance, which basically says, no, you're not just throwing some gravel down and calling it pervious pavement. It has to be, graded, and the subgrade needs to have minimal compaction, and it needs to have a rigid boundary around it if it's a granular material, and it has to be a reasonable depth, which will actually hold the 95th percentile storm, et cetera, et cetera. And so there's instructions for how to build and criteria for building pervious pavement, and it should meet those if someone's going to use them to get below a threshold. Swimming pools. In general, this question comes up because obviously it rains on top of a swimming pool, no water infiltrates, but it does, if they're built properly and plumbed properly, flow off into the sanitary sewer. And so essentially the answer is no, the surface of a swimming pool should not count as impervious area. And then gravel, I already talked about. Are public improvements included? I don't know whether this happens here. Situation, the developer comes in, has a private property that they're going to develop, and then the city or the governing agency requires them as a condition of that to also pave the currently dirt or gravel street in front of the property. So now their impervious area for their project goes much bigger. And I think the expectation there is that no, that is one project. It's, in all of the other reviews that you do for CEQA or whatever, you're considering that as one project because it's a project requirement. And yes, that additional impervious area counts towards the threshold. Now, when we get into the discussion of how to deal with roads, one of the things is, I have seen municipalities say, no, we will figure out a way to be responsible for the compliance for that street ourselves so we don't overly burden the developer of that site. And I would say that comes if you have a relatively small site and a relatively large amount of pavement outside. And so then you figure, oh, well, how the heck are you going to meet this 8% or whatever, your total impervious area, when you're on a small site? So there are ways of dealing with that, and we'll talk about it later. So any questions? I'm going to get into this next section of the principles of low impact development. Go through it. Yeah.
Real quick, I think that's a great discussion.
Uh-huh.
And the advice you gave in there was great advice. I just want to say from the big picture, it makes perfect sense. Oh,
Sorry, that's for you.
Oh, yes, me too. Thank you for that discussion of those thresholds and the requirements. And I just wanted to say that it makes perfect sense to me from the big picture, but I can see down at the low end of the threshold, it's maddening, right? You're dealing with pretty small increments, but you still have this same requirement. I can't see any way around it, but I just think we have to focus on working really collaboratively to find creative ways to get there, and that kind of gets to the numeric thing you discussed. So anyway, I look forward to more discussion on that.
Good. Yeah, we'll try to make sure we make time for it. Okay, so principles of LID. I'm going to go through this. Let's kind of rock through it. If anybody has a question or comes up with, gee, that's a confusing concept, shoot up a hand and we'll talk about it more. But this really starts with a problem of conventional urban drainage and the creation of impervious surface as a result of roofs and pavement, sometimes in just amazing amounts. Certainly the way that I think the way most civil engineers are trained was this idea of to collect and convey runoff, get it off the site. You don't want it, people wading in it. You don't want the water affecting your foundations. So get it off site. So the objective was to collect and convey. The impacts of this on the natural environment are actually pretty severe just by themselves. At the site scale, when you pave a site, it means you get higher peak flows. That can cause this kind of condition where no matter how much people go in there and try to do informal things to armor the stream, nature bats last and eventually breaks through it. The lower time of concentration creates flash flows, which can actually wash fish right out of the pools when they hit. You get runoff from storms where you never had runoff before. So if you get like a light drizzle in an urban environment, that means water in the gutters. If you're out walking in the woods, you'd never even notice that there was any surface flow. One of the things that happens that's an impact from being in an urbanized watershed is that the amount of time that streams are flowing goes up. And so the time you have moderate flows increases. So even if you don't have a big scouring flow, you get this situation where the steady erosion of the banks then causes them to fail at about mid-bank and causes cave-ins that way. So that's one of the ways that you end up seeing widening and down-cutting of streams when you have urbanization in their watershed. More runoff volume just means more pollutants being carried downstream from in an urban environment. The runoff energy means that you can move gross pollutants like trash downstream in a way that you wouldn't otherwise have been able to. Because there's less infiltration, you have less base flow during the non-rainy season, during the dry season. And then this last one, which is, I think, often overlooked, but it really relates to why we do LID, is that dry weather discharges, and particularly the small discharges that stormwater storm drains produce if you get a small storm in August or September, those flows can have very high pollutant concentrations. Either coming out because of urban slobber and people washing and over-irrigating and stuff, and those early storm flows. And that's the time that you actually see fish kills in streams as a result of stormwater discharges. You have high pollutant loads, particularly high organics, going into a stream which already doesn't have a lot of water in it and is warm, and it can be pretty devastating. So basically, what I want to point out here is everything we would do with LID just tries to reverse this process. You try to do on the site scale what it was going to address these effects of urbanization on the watershed and stream scale. So if we want to reduce peak flows, then we're going to detain runoff on site. We're going to increase the time of concentration by slowing runoff. We're going to let runoff seep away so slowly that it doesn't really affect the duration of stream flows. We're going to reduce the volume by infiltrating. We're going to reduce runoff energy so trash doesn't get flushed downstream, et cetera, et cetera. Generally, what this means for drainage design is we start out by minimizing imperviousness. We disperse runoff wherever we can, and then we direct runoff to bioretention facilities. And probably, that being the hardest part, we spend most of our time trying to figure out how to size and build bioretention facilities correctly. The advantages of bioretention, you get filtration and pollutant sequestration. These are a very effective way of treating stormwater. It's why we've moved to bioretention, or one of the reasons we've moved to bioretention rather than vegetated filter strips or vegetated swales or any of the other landscape-based treatment that we used to have. The idea is you want to capture that runoff, you want to hold it, and then you want to filter it through a porous medium, and that's the way that you get the maximum amount of pollutants out. Yeah. Yeah.
Yeah, I had a question about the sequestering of the pollutants.
Yeah.
So have they done studies now long enough to know what the final outcome of that is? I mean, if you're bonding pollutants with organic material or whatever, then what's the long-term?
Good question, and one that always comes up and never goes away, is what happens to the pollutants long-term? The answer is that urban pollutants arrive at the bioretention facility attached to sediments already. It's just fine sediment. So the idea is to trap those fine sediments and hold them. The amount that comes down is really, well, there's two things that happen. One is it tends to settle out right near the inlets. And when you do regular maintenance, a lot of that gets carried away just in the mix of mulch and dead plant, plant material and stuff, and is just taken away. And then the remainder becomes sort of integrated to the process of worms digesting your compost and sand mix over time. I have not seen any reports of any more than very slightly elevated levels of heavy metals, and they've actually found sort of quite a bit at the inlet, more typical of what you'd find if you took a shovel full from, up on the corner somewhere, and then decreasing as you move away from the inlet. Another advantage of bioretention is you don't get mosquito problems, as you can, particularly if you've used if you just moved clay soils around to make a vegetated swale, and often if they don't flow exactly right, and you get ponding. I know a couple of famous incidents where they ended up with both mosquitoes and macrophytes. You get the mimicking of natural hydrology, and I think ultimately the idea here is that we want to integrate our LID and make it part of our communities, something that's visible, something that's usable. And sometimes, of course, designed correctly, these can even be used as areas where people can have semi-active uses as well as simply the passive use of enjoying what they're looking at. And they tend to be very low maintenance. Now, if people want to do a whole lot with the landscaping, like any other high-intensity, landscaping feature, it can get expensive. But if you just want to put in some a no-mow fescue, or some coffee berry or whatever, and cut it back once a year and clean it up often enough so it looks okay, really the maintenance ends up being like what you pay for any other landscaped area. And they're easy to inspect, which is another big issue. Is there is, with subsurface facilities, always the out of sight, out of mind problem. The advantage of bioretention is you can just about drive by it, certainly walk by it, take a look, and in an instant get pretty much most of the information that you need to know as to whether it's working or not. So these are just some pictures of what bioretention can look like in the urban landscape. And what I want to point out here is that all of these have the same basic cross-section underneath, but you can make them look all kinds of different ways depending on where you are and what you want it to look like. So you can use it as a median in a parking lot. You can use it as a feature in a plaza. You can use it as a foreground to a building. You can use it as a feature in a curb extension as part of a traffic calming project. And when they're used in this manner, you have, I think, a feature which is both physically resilient in the sense that here's this planted surface, as long as you don't change the elevation and as long as you keep the plants alive, it continues to work. But you also get a social resilience in the sense that if it's out front and it's something that people feel some attachment to, then you have the idea that it's going to be continued to be maintained without a lot of resistance. Yeah.
Dan, what did you mean that these could be used as a playground area?
I'll show you the pictures. Yeah. So, and I'll get to that because I think it's the most exciting thing that's happening actually in bioretention is the idea that we could really create some facilities that are integrated into our urban fabric and serve double duty. And they both keep people educated and sort of build in their understanding about what it is that we're trying to do for clean water, and at the same time they can get other uses out of it. This set of pictures, what I wanted to show, this is early on when we first started doing bioretention in Contra Costa. These guys came up and they decided it was a good idea to spend their retirement savings to build industrial condos on spec. And it was about 2006, 2007. It was not a good idea, obviously. They lost pretty badly on this bet. And when I went by it a few years later, the site was abandoned. And obviously, try as it may, the city is going to find it pretty difficult to get whoever ended up owning that site, whether it was the bank or whatever, to be maintaining those facilities when there's no revenue coming from the site. What I want to point out here is that these facilities are
Dan?
still in place.
The mic's not picking up for some reason right now.
Hello?
There you go.
Is that better? All right. Okay. Sorry about that. So these are still operating. They're still capturing runoff. They're still filtering it through a porous medium. They're still removing pollutants. They might not be doing it as efficiently or as sustainably or be working for as long as they might if somebody was out there making sure that the plant stayed alive through the summer and cleaning them out every so often. But they're still somewhat doing their job, which would felt good that impervious surface is draining to something that treats the runoff. And then if someone finds a use for this project again, to renovate those is going to be really a pretty simple, straightforward thing. You'd go in there and take the weeds out, put down maybe some new sand compost mix and some new mulch, and plant it up and get the irrigation going, and you're back in business. So these signs are just to illustrate this thing of trying to put these facilities in the foreground, not something that goes in the back of the development. They're seen as a community asset rather than a utility which you want to put out of sight. And here's my park photo. And this is that's my daughter. This is right behind my house. And it captures runoff from my neighborhood. And this is a great grant-funded project. But this is a lovely area where kids play and people sit. It's very popular with the stroller brigade. And, you get a good hard rain, and most of that fills up an inch or two and then percolates into the soil. And so it's totally doing double duty.
Is it concrete wall?
You can see the slopes coming down on the side, and then the feature that you see up towards the stop sign there is a head wall. So that really provides the drop-off from the adjacent sidewalk there from the arterial street. And so it doesn't, another thing is the bottom doesn't look flat, but as we'll find out later, I made sure this thing was built flat. So its appearance isn't flat, but the bottom of it, you can see the runoff fills it right up. So a nice, attractive kind of community feature. And this one drains streets, but obviously on a larger development or whatever, you could have a private developer build something like this. So on to using the Stormwater Technical Guide. I got a time check. What time is it? And what? 9. What? 15 minutes behind? This is consistent. This is consistent at this point. Okay. I know I'm doing okay. All right, we're going to rock on through this then. So, using the Stormwater Technical Guide. I think I remember like maybe between half and 2/3 of the folks in the room have used the current edition. We'll just kind of go over, particularly for the folks who maybe aren't as familiar with it, what is in it, what is expected. So producing a stormwater control plan, one point here, it's meant to be a report and an exhibit. And often, if you're dealing with a planner, they're probably going to give you the report and not such a great exhibit. And if you're dealing with an engineer, they're going to give you an exhibit and you say, please don't make me write a report. But, but it's really meant to be both. And the reason is to both, first of all, show that we have those drainage management areas clearly defined, which is the main purpose of the exhibit. And that then also that we show that there's some thought given into how you can do as good a job as possible implementing LID, and how that fits in, ultimately then how that fits into showing numerically that you are meeting the requirements in the PCRs. As I mentioned before, there are 4 ways to follow these. The guide has step-by-step instructions. There's the checklist on page 3.2. We have a template, it's going to be updated, and then there's examples which will be posted on the Clean Program website soon. One thing that, again, I was mentioning before, that tendency to say, well, I don't know what's really going to be required, so we're just going to put something together and submit it and see what comments we get back. When I'm talking to developers, I say, try to make that first draft as complete and thorough. We would love to get to the point where the first draft is the final draft, or just about the final draft on the majority of projects. The template, again, sometimes I get feedback and say, oh, gee, how come we have to have a guide and a template? Why don't you just put the instructions in the template? The answer is that this process is really not about just providing information. It's not rote. It's not like just, doing something simple. The idea is we want people to use the manual as a guide in a creative design process, and then use the template just to format and consistently put forward what they've come up with. That said, that template, I think having all the information presented in basically the same format and the same order, certainly when I'm reviewing and I see a submittal and somebody used the template that I created, boy, I could just I could go right through. I know exactly where to find everything. So it's very helpful that way. I think there's nothing like a concise explanatory narrative that just says we're collecting the water here and it's going here, or here's why we did it this way, or we solved this problem in this manner. It really only takes a few sentences, and even for engineers like me, it's something that is often much more revealing and much more useful than just giving people a drawing. The other thing that I often see when I get submittals is I get a lot of extraneous information for some reason. I feel like, well, it's got to be really thick for one thing, as you sort of think, well, you got to pad this thing up, and really, you could do a pretty big project, with some complexity to it, and still end up with a stormwater control plan that's only 10 pages in one drawing. And that's what I like to see, but sometimes you see, they got some old drainage report on there, and they've got a site assessment, or they've got a geotechnical report, or one thing or another. And tell folks, well, you don't really need to put that in. If you could just tell us where we can find it, that would be sufficient. The steps in preparing a stormwater control plan. These are listed out on page 3.1, both in the existing edition and in the new edition. It's pretty straightforward, providing project data. I'll go through each of these, describing opportunities and constraints, doing a conceptual site design. In Chapter 4, we really get into the calculations and documentation, which is where it's shown that we're in compliance with the PCRs. Going through and listing the sources of pollutants and the corresponding source controls, describing what's needed and how stormwater facility maintenance is going to be done. I'll stop a little bit when I get to the section on construction cross checklist. We haven't changed what it is. We changed the title because it was a little confusing, and I just want to illustrate what that's all about. And then finally, the certification requirement. So project data, pretty basic stuff about just to understand the basics of the project. I just want to point out this illustration here in terms of what's expected, because often you see this done wrong, or you see that somebody has some difficulty getting there, is that these 4 numbers are all required. And this wasn't our choice. These are required by the PCRs, is that each of these numbers have to be provided. And I just want to illustrate how that works. If you had a site like this and it already had this impervious area built on it before you started, that is quite clearly C, so you need to have them do a takeoff on how much pre-project impervious area already existed. And then you have the new impervious area. So if they were building something that looked like this, yellow area, then that is a combination of the new and the replaced. So where it overlaps, and I can't draw with the laser because it doesn't show up on the television screen. If you follow the outline of where these overlap, yeah, here, thank you. So this right here is going to be the replaced impervious area, and the yellow area outside of that is the new impervious area. So they need to do takeoffs of both of those. And then if they're now obviously building over part of it and demolishing the rest of some of that existing, Then when they end up here, but they're leaving this, then that's the post-project impervious area. So it's pretty clear once you see it visually and think it through, but a lot of folks get it wrong, and I think if you're a municipal reviewer, you're going to end up in the sort of situation of having to explain this a few times. That net idea actually now can simply be shown as doing the algebra for this, is that it's the new plus the replaced minus the amount that you reduced the impervious area on site. Next area of project data is the information required by the PCRs for design, and there's really three pieces of it, all taken from sources outside of the guide and what we're providing. One is the watershed management zone. Those are on the Water Board's website, as folks probably know. The design storm frequency and depth, which can be gotten either by downloading a 384 megabyte PDF and zooming in on it and interpolating between the isohydral lines, or there's also a GIS layer if folks are using GIS. And then the urban sustainability area, and my understanding is that there are a couple of these in Region 3. Santa Cruz has one. San Luis Obispo has one. There are none yet in Santa Barbara County. So, but there may be in future, so that's the other thing that needs to be checked. Opportunities and constraints. Basically, is there anybody here who's actually done an LID design on a development project, been responsible for that? Okay, well, basically what the applicant's engineer needs to do at this point is begin to take kind of a squinty-eyed look at their project area and start looking at where the water flows and overlaying that in their mind with what the developer wants to do in terms of where they want to put their houses or they want to put their buildings or their parking lots. And then start looking for areas that are unbuildable for one reason or another, which are the best bets for where you're going to drain to and where you're going to manage your runoff. And often setback requirements are sort of your best friend in this case. The most obvious situation is if you have a street setback and the site drains towards the street, which is often a happy combination, because then they can simply take the runoff from the back to towards the front of the lot, intercept it there by keeping it on the surface, and provide the treatment in a bioretention facility right there on the street. Works out quite well for everybody. Often, if that's not going on, sometimes there are setbacks or easements on one side or another that are never going to be built, and that's a good place to think about putting a bioretention facility. Or there's an odd shape. There's an area where you're just not, because of the way the circulation happens or the way the buildings are set, there's a space where it's possible to put bioretention. We're also asked to look into factors that facilitate or prevent infiltration. I don't see this that often, that anybody's able to look at a site and say, oh, it's going to be easier to infiltrate on that corner than this corner. Doesn't happen, but if it did, it would be a good thing to look at. I'll just let that go in the interest of time. This conceptual site design process, in a way, in the Stormwater Technical Guide, we go over everything twice. In that, in Chapter 3, there's a whole description about basically what I was just talking about how to come up with a conceptual LID design for your site, figure out where you're going to disperse, where you're going to do bioretention. Sketch it out. That's really this part in this box. And then you move into Chapter 4, which is really this process of saying, okay, now that we have a general idea of what we want to do, we have something to start with. Let's do the numbers on it and figure out how it works out and whether things will actually fit. And of course, this process is iterative, because if this doesn't work, you got to go back. And to be emphasized is that all the way through this, the design engineer needs to be coordinating with the site design and the landscape design. I don't know whether in Santa Maria or other agencies you have seen the situation where you get a stormwater control plan submittal and it shows bioretention facilities on it or other facilities on it. And then you look at the landscaping plan, and it's not quite the same thing. And then you look at the site plan, and you know, the reason for this, I found out when I worked on the other side of the table, was the developer doesn't want to pay 3 professionals their hourly rate to talk to each other. So they will avoid having meetings between the architect, the landscape architect, and the drainage design engineer, and they will try to make it all work out in the end, and if it doesn't work out, well, then they got to go back, and it costs them more, and you wish that they had had a little bit more foresight, but trying to encourage them to do that. Yeah.
Speaking of which, is it still the case where you need to prepare this plan and submit it prior to the, for example, a plan development permit, the first approval from the city or the county? Yeah, I was going to say, if the answer, yeah, that's where most of us have a huge problem with, we don't get it. Here's the problem. So we prepare all this information, do this, it gets before the planning commission, they reject the project, or they modify the project in its entirety or partly, and you end up having to pay to have the damn plan done again. Now, a lot of times it's not a big deal. I just did a 6-unit apartment complex, $2,500, not a big deal. I got a 55-acre project that's got 500,000 square feet of buildings. That's a big deal. I don't know what that's going to cost me to develop. Fortunately, I talked the city out of the plan development permit at this time, but I mean, you're probably talking $50,000, $100,000, and there's no way that design is going to be used, because there's no way you can predict what's going to be built on a multi-faceted project that's 55 acres. So why are we not allowed to just simply get the necessary approvals from the county or the city and have a condition that we get approval from you for the design of the LEDs and the rest of it?
I'm going to answer your question in the generic sense from working around the state, and then I'll actually see whether maybe we want to see whether anybody from an agency wants to respond, or if they don't have to. But the reason for that is that often the critical point that makes the difference in whether you end up with a good design that benefits the community and saves the developer money, that decision point is before the lot lines are drawn, before the building footprints are decided. Once you have set those things, and then you move downstream and say, okay, so we're going to approve that the way that it is before the planning commission, and then we're going to follow up and do the drainage design later. If you're talking with LID, you often end up in a situation, well, gee, you approved a site plan with plenty of green space on it. Too bad all the green space is 3 feet higher than any of your impervious surfaces, and I've seen that happen. So.
Why should that not be the developer's choice? Why, I mean, if I'm going to pay for it twice because I screwed up the first time.
Yeah.
I'm saying it needs to be the developer's choice. If I design my site and it doesn't work for the LED and I've got to do it twice, that's my fault and I'll take that risk. But why should I have to prepare a plan that I know I'm not going to use and pay for it and then pay for it twice?
Well, frankly, I'll be very honest here. The politics of the situation is that practically what I have seen over and over again around the state is that when that happens, you end up with an agreement. Oh, well, we'll let you do an underground vault because it's impossible to do LID with the site design that you already got approved, and it would be too much of a burden for you to have to go around and have to redesign your whole project and go through the planning commission, which may not want to see you again anyway. So that's the problem. And so I think the answer to this, what really does work, is to have a really functional process where you have a pre-application meeting, you have an understanding with staff ahead of time about how this project is going to go and how it's going to be integrated. And by the time they go to the planning commission, they pretty much know, yes, we have an integrated design and this is something that they're likely to approve. If you have a situation where staff goes to the planning commission and they often don't know what they're going to do, then I really sympathize with you. I would not want to be in that situation as a developer. Yeah. Anyway.
what this brings up is the importance of not only the, like, for the city of Solvang, for example, the public works staff reviews all the stormwater design. But we're working with our planning and building staff to make sure they're educated and understand this process, so that when a project goes to the planning commission, they can explain and educate the planning commission that, like you said, I like that word you said, an integrated design. Because you know, what's going to happen is, if you don't follow this procedure, looking at the stormwater issues up front, very early, basically as the first kind of controlling factor of the site, that determines if the site's a round site, a square site, or a triangle site. And then you design your buildings and your site plan and your layout to fit a circular site or a square site or a triangular site. I don't know if that analogy makes sense, but the stormwater conditions and how you have to handle that, that has to dictate how the footprint of the buildings and where you put the parking and stuff. And on one of your earlier slides, you brought up if you have an odd-shaped site, that's like perfect, because you're going to have these odd areas of islands in the parking lot, landscaped islands in the parking lot, and landscaped areas between the buildings and the parking or whatever. And the stormwater design basically now, with these requirements, is controlling. It's the controlling factor. So if you don't look at that, you're going to end up exactly like you said, with kind of this half-baked thing, where then you go, okay, and you have to compromise and accept a bunch of stormwater stuff at the end that isn't really what you want. It's not really the ideal situation, and you're stuck kind of like trying to compromise with the developer at that point instead of doing it right from the beginning.
That's my experience. So I realize that might not be a totally satisfactory answer, but yeah.
Yeah, with most municipalities and cities are real good about this. I mean, I go before the planning commission, I know that it's going to be approved, so I don't mind doing it there. In the county, for example, that's not the case. I mean, they'll sit up there and they'll relocate a building, they'll move one building, they'll have a different place to where, John, you've been there forever, right?
Thanks, Dan. And you said a regulatory person could address this, so I'm happy to do my best. In fact, I got to, before I even speak, say, Dan, correct me if I'm wrong, Mr. Blau is a planning commissioner with the county. So when he said they, he meant we. No, I know, but you collectively. The way I mean, as you said, an integrated plan, and as you said, the difference between a small project and a large project, it seems real clear to me, and I don't want to say this is how we do it, but I'm pretty sure this is how we could do it and can do it, and do it from time to time. We take a project of any size. That's one of the challenges, is a small project here gets scrutinized as if, regardless of its scope or scale. I think we work to make sure that this issue is addressed in terms of order of magnitude, or that the scale works, and then when the Planning Commission or the BAR gets in there and start moving things around, you still know that you have a plan that you can work with, or that you've, as you were saying, you've kind of scaled your project for the site. You know what its general shape and density will be. So that's my answer, and I think that we've done that. We get a preliminary plan, allow it to move forward to the decision maker, with a requirement that the decision maker can approve the project, and the plan will be finalized without coming back to the decision maker. And I know we've done that a few times.
That's not the rule. They started out doing that. They were actually putting this as a condition of approval on the projects for PD. And I said, wait a second, where's the stormwater plan? So we don't have one yet.
Was that in the last 10 months?
It was 10 months or so ago. Well, my point is, if you ought to be able to tell that in this 50-acre parcel, I'm going to be able to comply with all this. I mean, it's not like it's a site that's constrained. Well, I don't like the idea of spending $50,000, $60,000 twice. And that's what's happening.
We need to move on.
Yeah, and I apologize. interrupting your presentation, but I think, thanks for coming to North County. And it is for us, for sure, I can assure you of that. What was I going to say? I lost my train of thought, but I really hope when Kathleen's in the room that we will come back to this at the end of the presentation, because she's actually the whole time been kind of in that position. Yeah. Yeah, please do.
Great. What we can do here, and certainly in the role that I've tried to play, is to make the process of getting from your site plan, landscaping plan, basic concept of what you want to develop to a stormwater control plan as simple and straightforward and easy as possible. So at least, if you have to do it twice, at least, we've shortened the process of what you have to prepare and submit by as much as we possibly can, and giving you the tools to simplify that. So I'm going to pick up a little time by going through these processes of analyzing a project for LID pretty quickly, and then we'll have to do a time check and see whether we need to cut. So this process of optimizing the site layout, really it works best if you have a lot of space, but the idea of just trying to minimize the overall amount of imperviousness so that you reduce the total amount of runoff that you are creating from impervious surfaces and that have to manage, just generally a good first step. Using pervious surfaces, what I will just say about this is my experience as an engineer, being mindful of costs, these are really good things to do if the owner developer wants to do them, because you can get a lot of stormwater benefit out of them. But they are not the cheapest or most cheapest to maintain solutions. They're really beautiful, they're great to do. If somebody wants to do them, I would encourage them, but pushing someone towards them as the best way to do this, not necessarily productive. What is productive is getting people to disperse runoff and to go from this collect and convey concept to what I've heard described as a back to the future concept, the way that we used to do things, of simply trying to disperse runoff off of our driveways and roads and parking lots, and push it off into the bushes, into the landscaping. By far the most sustainable, cheapest, best way of doing things. And one of the things that we've been working with the board on even now is figuring out how we can ensure that that is properly credited with the limits that they want on it, and we'll get into that later. Harvesting and use, I just want to point out here, you may get the question, why don't we just capture this water and use it? Why wouldn't that help us meet our stormwater MPDS requirements? Point being is the amount of water that you could feasibly capture on site or would want to pay to capture on site and reuse. It's a great thing to do. It helped this project get LEED Platinum. This is a city recycling center in El Cerrito, where I'm from. But when it came to actually looking at the amount of water that you wanted to treat, they built a bioretention facility here downstream from it, which was sized the same way as any bioretention facility would have been sized. The reason is you got to worry about the big storms, and the big storms come typically when that thing's already full. So you don't get a lot of benefit on the treatment side from diverting runoff for reuse. So the answer here is that we're generally in an urbanized area. We're talking about most of our impervious areas being directed to drain to bioretention facilities. And again, the reason we like these, we moved in this direction from all the other landscape-based forms, is these capture the runoff. You can put a lot of area into them. They pond it, they filter it through a porous medium, and they promote infiltration into the soil below. So you get the combination of the treatment and the retention and infiltration. And then where you don't have the capacity to infiltrate, you get treatment before discharge. Source controls, there's Appendix A to the Stormwater Technical Guide. Basically, the idea of that is not to take that appendix and simply copy it and staple it to the back of the submittal. The idea is to go through it and check off which of the potential sources of pollutants that are listed there are on the site, and then show the corresponding source control that goes with it, which is specified in the appendix, and then fill out this column. And then there's also some sort of operational BMPs, which not really enforceable through the development review process, but are things which are put on there as things stormwater coordinators will want to see done over the life of the project. So these are some of the common sources that you would find in typical commercial projects: a food service, the trash storage area, and then if you have any loading docks or material storage. So on the maintenance side, this can often be kind of a complex, for some projects, particularly subdivisions, it can get very complicated and can hold projects up in terms of the question of who's going to be responsible for owning the bioretention facilities and managing them in perpetuity.
Dan, as far as source controls, what are you typically seeing people doing with truck docks? Are they plumbing them to sanitary or to storm drain through pretreatment?
Loading docks are one of the toughest because they tend to be depressed, and so they're capturing runoff. And what you do there, I have seen some municipalities actually approve a valve in there, which is then opened when it starts to rain and is otherwise closed, so anything that spills doesn't go down there. But generally, the simple, straightforward things are to make sure that the loading dock is covered. And so you're not out there moving materials around and stacking them on the dock up in the open air. And so it requires a roof over, of course, high enough that trucks can pull in. And that basically the loading, unloading operation there is done essentially indoors rather than outdoors. So on the O&M, there's really two pieces of this. One is to say generally what needs to be done. You can almost, for this level of detail, cut and paste what's already provided in the Stormwater Technical Guide. If you're talking about bioretention, basically there's a schedule in there. Check after rainstorms, clean out the trash every so often, and then maintain the plants on a schedule which is normal for that kind of landscaping. Typically, if you use a native plant landscaping, when I've talked to landscape architects on this, is essentially an annual maintenance cycle is all that they really need, and so you can have like really low cost maintenance on these facilities if necessary. But the harder part is who's going to be responsible, and the PCRs do require that be very clearly defined. Relatively easy for a commercial development where it's one owner. Gets a lot more complicated for subdivisions where you're going to have different property owners, and you need to make sure that with the successive iterations of who owns that property, particularly if it drains, somewhere as part of either a commercial development like a shopping center or as part of a residential development like a subdivision, that responsibility runs with the land. Typically, does Santa Maria use a standard agreement for O&M? That's pretty much goes that same basic process. And then the stormwater control plan needs to include a statement that once the facility is built, that the contractor and the original applicant will be responsible for ensuring that it's maintained right up to the point where it's transferred and moved into your longer-term operation and maintenance verification program. I'll talk about this construction cross-checklist just briefly because sometimes there's confusion about it. And this is really to address this problem, which has been noted, is that once you get a stormwater control plan approved at the discretionary approval point, when the planning commission or whoever goes on it, and then the point where construction documents are submitted for building approval. And I think folks know that that time frame can be weeks or it could be a year, depending on the circumstance, and people come and go and they change jobs and people forget things. And so the idea of this cross checklist is to give a quick little summary of what is in the stormwater control plan at the back of the stormwater control plan, listing the description of each BMP which needs to be followed up on, the page of the stormwater control plan on which it appears, and just those two columns are filled out and put in the stormwater control plan submittal. And the idea is that then what the building department, the plan checker should be looking for is this same table showing up on the plan sheet with looking the same as it did in the stormwater control plan, but now with this column filled out to say what plan sheet the reviewer needs to look on to show, oh, that's where they showed the bioretention facility, that's where they showed the roof over the loading dock, et cetera, et cetera. That's where each of these things are taken care of. And then finally, the certification. Does the city require a PE to do this, or can it be a architect or landscape architect? It varies from jury. Okay, design professional. Okay, that's a good choice. Okay, how are we doing on time? Okay, we've used the time. It's now just about time for the break, right?
Yeah,
Is it?
yeah, if you want to roll this one and the design, construction, and maintenance, do you want to roll those together right after the break?
Yeah, let's take Jeff's question and then we'll take a break, and then we'll figure out how to roll those two together.
Just two requests as you're updating the stormwater technical guide. We've had confusion with just consistency with the permit, like the tiers. Our developers are getting, like, because in the permit it's called what is it, performance requirements. So it's a minor thing, but we always tell people to go check, follow the permit. That's the, anyway, so the tiers have been confusing for some reason. And then also we've been really stressing the watershed management zones up front. And I know you do touch upon them in the stormwater technical guide, but we found that that's something that really dictates the whole process. So we've just been trying to elevate that in the stormwater technical guide.
Let me ask you, do you end up with different storm depths depending on where in your jurisdiction in Monterey County you are?
Yes.
So that's yeah. And writing this for Santa Barbara County, it was like, didn't pay a lot of attention to it because it's always the 95th percentile storm. So, but we can make sure that, so when we adapt it, it deals with that a little bit more explicitly. All right. Okay, so we will take a break now. I'm sorry to shorten it to 10 minutes, but let's start at 25 minutes to 11. We will reconvene and continue. Are we on? All right. Okay, let's keep going. We got a little bit behind. I think we had some very productive discussions, so I'm glad that happened. But I do want to make sure that we have enough time for Tony to demonstrate the calculator, because I think that'll be pretty useful. So I'm going to go through these next presentations. And again, if anyone has an urgent question, shoot up a hand, but I'm generally going to try to keep up a pretty good pace. This next section is about documenting LID site design. This is chapter 4. So we've done chapter 3, basically, where you kind of come up with your concepts, you figure out how everything's going to work together, you try to do your basic integration on a conceptual level, and then this is getting into the question of transferring that design concept into numbers which demonstrate compliance with the post-construction requirements. So step by step, the steps here are to delineate the entire site. And again, this is sort of the key point here, is delineating the site into DMAs, categorizing and tabulating them, selecting and lay out LID facilities, using the calculator. Again, we're putting even more emphasis on the calculator for both Tier 2 and Tier 3 projects, and then iterate that process until all your facilities meet or exceed the minimum criteria. So this concept of drainage management areas, just to illustrate it here, is really it's starting from LID site design principles, right? We want to disperse runoff rather than collecting and convey it. If we were doing that in this sort of circumstances, you know, our idea here is we don't want to concentrate runoff. We want to keep our drainage areas small. I had a conversation during the break. That often means you end up with a lot of drainage management areas, which just gives you something you have to sort of manage, and Tony will show how that's done with the calculator. So if we had this, and you basically transfer this idea of dispersing runoff into the areas which are running off in different directions, this gives something that looks like a hip roof, hip roofs do a great job of dispersing runoff, and we put that hip roof building into a parking lot, and then follow the grade breaks to show the division of the other drainage management areas. And here now we're up to 7 drainage management areas dividing up this site. I want to talk a little bit about this 8th one, which was kind of in our hypothetical example here, the one that's being left alone in its natural condition, or at least not being anything built on it. So we've identified our setback areas as possible bioretention locations. In drainage management area 8, really you have a few different options of how to handle runoff in a situation like that. It could be self-treating area, it could be a self-retaining area, or you could drain it to a bioretention facility, which is sort of your least best option of the 3. So here I just want to illustrate what the difference between these concepts are. Self-treating means that this area drains directly to the storm drain system. Our argument here is it's not picking up any more pollutants than it did before you built the project. It's not producing any more runoff than it did before you built the project. So basically, it's okay to continue to let that flow out to the curb, or even to pick it up with an area drain if necessary. This contrasts with the idea of a self-retaining area, which is something that you might want to do if you were doing a landscaped area more interior to your site, wasn't a direct path to go out to a storm drain. And often the easiest thing to do there is just to grade it a little bit concave, very subtly. The idea here is that if it has an average 1-inch depth over that landscaped area, so it's just kind of like this, it comes out to 1 inch on average, that can take a 2.4-inch 24-hour storm, or it's a 48-hour storm, and produce no runoff from it. And we actually did the continuous simulation modeling to show that that was true. And then the third option would be to drain it to a bioretention facility, in which case we give a very generous, I think, runoff factor to account for how much water is reaching it. We can be generous because we're lopping off the 1/20th most intense storms by definition, or actually for the 85th percentile storm, even more of the storms. And so we're only talking about small storm hydrology, so we can justify using a lower runoff factor. Again, to illustrate these same ideas in cross-section, here in a self-treating situation, runoff towards here, we don't want to allow runoff from the pervious area, from the landscaped area, onto the impervious area where we would then be collecting sediment, which is then going to flow into our facility, and which we would require us to handle that. Instead, we keep the drainage from pervious and impervious areas separate, and we could even pick up the drainage and take it to a storm drain if necessary. That's self-treating. For self-retaining, we do something a little different, and here we're showing having this very gentle, subtle depression. Now, one thing to note, and this goes with this idea of dispersion being our best option for handling runoff and using it wherever we can, is that we can take runoff from roofs or paved areas, and we can put it into one of these in a subtle, informal, don't get too exercised about the engineering details of it. We're trying to make this a simple thing where it just goes off into the bushes. But we do put, just for the kind of a check to make sure that nobody's going too far with this, a limit of 2 parts impervious to 1 part pervious on there. So you can take 2 parts of roof or paving, 1 part of landscaped area, do this subtle concave grading, and say that we've managed it. There's no requirements for, putting this in our operation and maintenance verification program, and you're not building an engineered thing that costs money and needs to be maintained. So where that can be done is the best way of handling runoff. Now, I did get this question about why so many DMAs, and this just kind of illustrates, well, you could perfectly well, since they're all going to the same facility here, you could simply combine them and call that one drainage management area. The reason you might not want to do that is as if after, in your iteration of your design, you wanted to take this little area here and make it go off that way instead of this way. If you are set up with all 50 drainage management areas or whatever you might have, as Tony will show you when you use the calculator, it becomes very simple to iterate your design and do subtle changes in where your runoff is going in order to come up with an optimal design once you have it set up. Yeah. Microphone in my hand.
Can the self-retaining areas be scaled to, say, a Tier 4 project? So if you say have a 6-acre site, you pave 2 acres, and the rest of it is able to drain to the other 4 acres, can you keep a self-retaining area, or do you have to go to bioretention?
Good question about how self-retaining areas apply to Tier 4, and we were actually, Tony had raised this with me just like a week ago, right? And the answer is for MPDES, great, right? But we're not the flood control folks. And so I think it's a perfectly legitimate thing to do from everything that we're looking at in terms of meeting the Tier 4 requirements that are in the PCRs. But remember, those are meant to dovetail with what the flood control folks. The thing about the flood control folks, they're worried about what happens when it's been raining for 2 weeks, everything's totally saturated, and no water is, going anywhere except into the creeks. And so they've got a different set of concerns, and we kind of leave that call to them. So, thing about drawing DMAs, and again, having this conversation during the break about what it takes to do this and to follow it up in the field even during and after construction. The idea here is that as we draw these and as they are built and as we follow up on everything, when you consider a DMA and you're drawing it, pretty much the way this is going to work is that it's always going to follow roof ridges and then the grade breaks and the pavement around, divide your site up into separate areas pretty naturally, and then in your design what you want to do is to try to make this distance between your drainage management area and your facility as short as possible, because particularly on a flat site, you need to worry about how much head that's going to take up if you have to be transporting water from one place to another. So your basic kind of concept here in trying to make this whole thing work is to try to break the site up into DMAs and then have pretty frequently interspersed facilities throughout the site. Once you've gotten to this point, then it should be pretty straightforward to do the takeoffs of the number of square feet in each drainage management area and tabulate those, and now you are set up to punch things into the calculator, which Tony will be covering later. My arrows here are showing the linkage that you would establish between showing how each drainage management area is handled. And once you select and lay out your facilities, and again, talking about that question about how much engineering you have to do, you have to get this far. But then, basically you need the next step is just simply evaluate how much of a footprint you need so you can show when you do your submittal that you've set aside enough space realistically that you can meet the requirement in the PCRs.
If that would have worked for the submittal, no problem. That's not an expensive thing to develop, but so if that's it, great. And all the other little issues and how we build things is the other issue that's difficult.
That's great to know. That's a great clarification. So for parking lots, again, this using the median strips. Now I will point out here that I was very happy on the day a little more than a decade ago, the first time I laid out a drainage management area and figured out how I could locate a bioretention facility, because it was this one right here, and the 4% using the dog bones on the end worked out perfectly. And it's worked everywhere in the state, and from that point, I made it my mission to get written into permits that 4% could be used, and I was successful everywhere in California except the Central Coast, where we have to go to 7% typically as a good, just as a rule of thumb, as you're doing your iterations with the calculator, that's a good point to start. And you look at that and you say, oh my God, that's too deep. And so you make it a little larger and it comes up shallower. Or you say, well, I could go deeper than that, and you go down to 6% and you see whether your excavation is so deep that your trenching is going to drive you nuts. So on a commercial project, this one is one that is actually going to be one of the examples that's going to be posted on the website shortly. This is a drive-through with a little parking lot and plazas and a little building here. This was actually constructed in San Jose. At the time, it was to be a Starbucks. I looked the other day. It's no longer a Starbucks. Now it's a Chipotle. But the bioretention facilities are still there. Yeah, exactly. Yeah. Building for the long term. So what I did was to take this, which was developed for that 4% sizing factor, and see what happened if we plugged this in using the PCRs. And the answer just here is that these two worked out just fine, reasonable depths. This one, which drains this whole area here, ends up being pretty deep. You end up about 5 feet of depth. If you just use gravel, you could obviously make that smaller, either by using our facility with the orifice, or by possibly putting in buried pipe or something in order to create more efficient underground storage inside that gravel layer. Wanted to point out, when you're doing design for something like a gas station or an industrial type facility, the big problem in locating bioretention is that it tends to conflict with vehicle movements, and people want a lot of open paved area so you can have cars going in different directions. Same thing if you're doing an industrial site where the trucks have to move around and they really don't want any breaks in it. So in this case, the idea is to move the drainage off towards the back of the site and put the bioretention out in a back corner. On this one, I just like to say this was rolled out in front of me during a meeting with some city officials in Contra Costa City. The developer was there and rolled this out and said, see, there's no place to put any bioretention. Mm-hmm. And this goes back to the whole point of, well, if you were going to put bioretention on this site, you sure would have wanted to do it before you drew all the lot lines. Because the best way of doing this is to basically take the same design, take a little bit off of some of these lots, make a separate commonly owned lot, which is a much better bet for ensuring that you can set up a maintenance regime which is going to work. So you're not going on and dealing with individual homeowners to get your maintenance done. Have it done by the HOA or by a common agreement among a set of homeowners, and fit it in there. In general, my advice on engineering drainage for subdivisions. Drain a portion of the roof runoff to the rear yard, direct the remaining runoff to the street, and then drain the street to a commonly owned bioretention facility. About one facility for every 6 to 10 lots seems to work out pretty well. This is the example that Tony will be showing you, with the roofs going off to the backyard, the driveways and the front roofs going to the street, and then the street draining to 2 bioretention facilities put out on the main arterial where they can be easily inspected and in a commonly owned and maintained area. So that was the break that we already had. Let me get into bioretention design and construction, which, yeah.
Have you had any issues with the HOAs?
Oh, sorry.
Have you seen any issues with the HOAs maintaining the bioretention areas in perpetuity? We've been hearing that they can transfer, if the HOA dissolves and they reestablish, that they can transfer responsibility. Has that been an issue for anyone?
I've heard that expressed as a concern. I'm not familiar with cases where it's actually happened. And I think, part of that is sort of updating the way that we deal with HOAs, because I think once upon a time it was, oh yeah, we'll just let the homeowners deal with it. And now I think a lot of cities have learned the hard way that there's some developments where you don't want to allow that to happen that way because they're too small, or you just don't expect that HOA is going to last forever. Obviously, if you've got hundreds of units, then it's a lot more likely to survive.
If you have the opportunity, the best thing to do is get a landscape assessment district, maintenance district, and let the city own it. And that's what I've done with a lot of them. It works out wonderful.
Yeah, good solution, yeah. So getting back into drainage design, this is my friend Dan Freeman. He's a developer in Contra Costa. And this is a house that he had just built. This was in 2005 or 6. And we were just learning about this bioretention business. And he had hired an engineering firm, and a young engineer had taken the elevation of the downspout on the back side of this house, which they had decided to drain to the bioretention facility, and had laid it out at a 1/4 inch per foot drop. And then when he figured out what that elevation was out in the front yard where the bioretention facility was to be, that's the elevation that the bioretention facility was built at. It actually got approved and built. And the reason Dan is so unhappy in this picture is because the potential buyer had just come and looked at that house and said, I'm not going to spend $1 million on a house with a pit in front of it. So he was on the bleeding edge of this. They did eventually re-engineer this. They tight-lined that downspout and used it to bring that drainage right out here and bubble it up to a level elevation which is just right at close to the street level, and rebuilt that facility, and he sold that house for what he had expected to sell it for. So lesson being, keep your drainage on the surface. Use sheet flow, use valley gutters, use trench drains, use anything, even if it's a little bit more expensive, but don't put it down in a pipe unless you've got a steep hill and you have the idea that you're going to collect all that runoff and then you're going to disperse it, that energy again, and put it in a bioretention facility further down. This is my mantra here, the thing I repeat over and over: flat, flat, flat. Bioretention facilities need to be built level on each layer, and the idea is that is how we get so much hydraulic effectiveness in such a small space. Is we collect all that water, we pond it up, we hold it, and we make it go down. If this is tilted at all, like this one or like that one, these are built. If you're familiar with sand filters or you ever worked in a sewage treatment plant, this is like pretty much a good design for a sand filter, is to get the stuff through, collect it on the bottom, and get it out of there. And that was a design. That's not what we're doing with bioretention. We're trying to hold it in one place, and so the idea is that we want these things to be flat at the bottom of the excavation, flat at the top of the gravel, and flat at the soil layer. So during the construction process, walking around with a setting up a laser level and walking around with a rod is a good way to check that and make sure that everything's at the same elevation. Here's the same thing going on with the soil layer. Often get this question is, gee, can you really put a bioretention facility next to the foundation? The answer is yes, you can if your foundation engineer says that you can. And some foundation engineers will, in certain circumstances, say that you can. I'm not a foundation engineer, so I really can't say why they don't, but this is really just to sort of, for folks who are in the business of trying to get these things in the right places, is that it can be done. Often it means moving to a heavier foundation, substituting a mat foundation for footings, whatever it is, but these guys can do this. This is in shrink swell clay soils. This is also in shrink swell clay soils. What I want to point out here is the error on this project. They got this side right where the building foundation is. What they didn't anticipate was that this street is going to fall into that excavation eventually, and they ended up putting in, what do you call it, little wing walls or whatever to hold up that wall. Here's another example of the same thing being done with these little bridges to ensure that the bioretention facility walls don't start turning inward. One way of handling this is generally, both for pavement and for buildings, is an impermeable liner put on the side facing the structure that needs to be protected, not on the bottom. It's continued to allow to infiltrate that way, but this just keeps some of the moisture from going there. It's the sort of geotech's general first solution to the problem of protecting structures or pavement from water from bioretention facilities. I like to show this site. This is on a very steep slope in Martinez, unincorporated Martinez. And just to show that this is how steep the site is. And here's a bioretention facility perched way up on the hillside, built nice and flat, no liner, allowed to infiltrate, engineered fill, historic landslide. It can be done. You know, the engineering firm that did this, the Geotechs, they are the biggest and most respected firm in Contra Costa. So this is it right here. And you can see the street goes down like that. There's that house. You know, so he's got one of these walls. This isn't the same one, but he's got one of these walls between the bioretention facility and the down. So it just requires enough concrete. Yeah. You know, just make those foundations big enough. High groundwater, another issue. Just pointing out that the PCIs require a minimum 6 inch. 6 inches and 24 inches is what we're looking for here for the bioretention. And so, as long as your groundwater isn't too close to that, the issue of having a groundwater mound underneath these and potentially not having a lot of distance here really isn't an issue. So if you have groundwater and somebody says, oh, I got groundwater within 10 feet or I got groundwater within 7 feet, as long as this isn't extending right down into where you expect the groundwater to be, I wouldn't worry about it. I'd say go ahead and use this. It's still a great solution. You might end up with some less effective infiltration during the wettest periods, but, so what? Same thing with no storm drain is just to point out there's the potential, depending on the circumstance, to, if you have enough head, to connect that under drain out to the curb or to daylight it. I know that in some places, been given the example of Isla Vista, which I went and drove around yesterday. It's like, oh yeah, there's no storm drains, and all the sites are really flat, and so the answer there is going to be that you have to build these without under drains, essentially, because there's no place to tie them in. Fortunately, in Isla Vista, I don't think you'd have a problem, very frequently have a problem with one of these that didn't drain, because the soils there seem to be pretty well draining, which is probably why they built it like that in the first place. So the way to get stuff built flat, I showed you during construction the way to ensure that they actually build them that way. In design, the way to make sure that this happens, I found, is to call out on the plans rather than on a cross section, and get the numbers on the plans saying the elevation of the, here it has BGL, bottom of gravel layer, meaning the bottom of the excavation, the bottom of the soil layer, meaning the gravel-soil interface, the top of the soil layer, meaning the top of the bioretention facility, and then the top of the grate, the overflow grate, and the curb around it, and have all those called out on the plans. It's been suggested to me that on top of this, the plans can also say in a note, build it flat, it's to be flat. But this way you've got that elevation, you can ask during construction, you can ask the contractor what reference point he's using, do your little calculation, and then have them walk you around with the rod and show you that you're actually building these things at the right elevation and at a consistent elevation throughout. For the overflow structure, this is an interesting back and forth. I have people saying, oh, I really wanted to use an updrained piece of PVC, put it there in the field, and then I want to come in with a Sawzall and saw it off and put a hat on it, and there's my overflow structure. It's not necessarily the wrong way to do it, but it's, I think, probably less resilient, less sustainable than putting in a concrete catch basin, which is a better, I think, a better solution. If you have an overflow elevation at a particular point and you have this spec and these guys come out in the field, you have a fairly good idea they're going to take their time and set it at the right elevation. And once they've done so, that over the life of the project that it's not going to move. The downside of this, and this goes with having lots of drainage management areas and lots of bioretention facilities distributed throughout the site, which you really want to replicate the natural hydrology. However, if each one of these has to have a catch basin, the catch basins are about $10,000 a piece installed, and that's just going to be a cost item, depending on the circumstance and depending on the project context. But it's just a trade-off there to consider. It's one of the reasons that I think there is sort of a happy best size for a bioretention facility. I like to think that it's somewhere 800 to 1,000 square feet with the tributary area corresponding to that. Comes up with a good design, but certainly you see them a lot bigger and you sometimes see them smaller too. Bioretention edges. We put this into the guidance. This is in the plan view of the bioretention facility. And this just shows that we like to have a clear delineation, something structural that shows where the landscape, the conventional landscape soil stops and the soil mix of the bioretention facility starts. After all, these are engineered facilities which municipalities are on the hook to ensure are maintained, stay where they are in perpetuity. You would like to have pretty good delineation out there in the field of where they are so you know exactly what you're looking at over time. So simply putting a landscape timber or even better, a concrete curb in this photo, that would be like along this line here. This is conventional landscape and the bioretention facility is out there. Gravel and underdrain. Main point here is no filter fabric. I don't know whether you're still getting applications or engineering drawings that show filter fabric in there. I'll just tell the anecdote that back in Prince George's County, Maryland, where the term LID was first coined, and they started building these things back in the 70s. And they got a US EPA grant to go dig a bunch of them up and see how they were operating after many decades. And about half of them were performing, even though they hadn't been maintained a lot. They're more or less exactly as well as when they were installed. Half of them had failed, were no longer draining. The reason, almost all of them, in the cases of failure, was because there was a layer of filter fabric to keep the soil from migrating down into the gravel. It had gotten biological slime on it, had gotten clogged, and had stopped. Biological slime, it's great stuff. It processes pollutants. But it also clogs things and keeps runoff from getting through. Building the underdrain, after my experience on this particular project, What I like to see, and the way that I'm recommending this be done in the design stage, is you've got your level of your top of gravel layer, and you set the under drain right on top of the top of gravel layer. So you dig a groove with a shovel, take the holes facing down, set that on the gravel layer, and then backfill over with the soil compost mix. This way you are ensuring that your holes in your perforated pipe are embedded in the gravel layer, but at the same time you are getting every inch of storage that you can get out of there, so you're not really wasting any of your excavation just in order to bed the pipe. Planting medium. I don't know whether folks are having any trouble getting this stuff now. What happened in the Bay Area is actually the compost market has been turned on its side by the demand for bioretention, because there's so many facilities going in, is that it's affected the cost and availability of compost. But the key thing here is this mix works to have this concentration of runoff going through it over and over again, only when there's no clays in it. If you mix clay and sand, I don't know if we have any gardeners here, but you put water on that a few times and it turns into the most amazingly impermeable material that you ever saw. And so that's exactly what has happened actually when we've had clays contaminating the mix. And so folks will always say, oh, well, can't we put a little topsoil on top of this, or can't we add this, or can't we add that? The key thing is that as soon as you start putting any clays in there, you're taking the risk that it will fail. Often, you know, when you get into a discussion with a contractor or an owner on this, and they say they want to do that, you say, well, you know, the problem with that is that if it fails, it's going to be your cost to go and tear all those plants out, excavate all that material, haul it off-site, haul in new stuff, reinstall your plants. You know, if you want to take that risk, that's going to be on you to set it right, because it's, of course, the city's responsibility to ensure that it continues to perform. The question about whether you can grow plants in this material, I think has been pretty much settled. It works. It works pretty well. You just have to have the right plant palette. Obviously, if you have no irrigation, your plant palette gets pretty restricted because you have to have stuff that's going to survive in very dry conditions. With irrigation, what you want to make sure is that you have an irrigation cycle that can be set separately, so you can irrigate frequently and less, more like you would be if you were growing plants out in the desert with drip irrigation, which is frequent cycles so stuff doesn't dry out, and so you're not allowing the water to just simply perk down. And then finally, on avoiding design conflicts, I just like to show this photo. This is a bioretention facility, takes drainage from this area. This is what happens is that, you know, the utilities, they don't want to say where they're going to put their stuff. They want to come in after everything's constructed the last minute and say, oh, we'll find some landscaped area to put that in. And so the landscaped area they're going to find in developments nowadays is often your bioretention facility. And so here, obviously, after this was designed and sized and everything, it was decided to put in a backflow preventer. Undoubtedly, there's a pretty big foundation on that, a hydrant, another hydrant, and a stop sign. I think it's pretty much filled in what was going to be a bioretention facility there. So the lesson there is make sure that the utilities are going somewhere else. You often see the cable companies want to put you know, their box in your bioretention facility. Not such a great idea. So I want to point out Appendix B. That is a checklist which was created by probably the person with the most experience that I know of in supervising the construction of bioretention facility in Walnut Creek, where they've had a lot of development. They've been doing this for a long time. So this very much came out of a process of learning and experience, and basically it has the things that need to be checked at each stage of construction by an inspector. The problem of how you figure out who's doing the inspections, that's city by city, right? Yeah. So just to say there, yes, inspections are needed. If you want these things to be built right, you have to put somebody out there on site who's individually familiar with what it is that you're trying to do and able to get it done right. I recommend that, and this is something that's really just between the owners and the contractors, not so much that the city can necessarily make happen, but I just recommend a 2-year warranty. It's a standard warranty on landscaping is 1 year, but it really helps to have a second season and make sure that if you were going to run into the problem of the soils freezing up or something, that you had the opportunity for the owner to make sure that got corrected at the contractor's expense before the contractor's entirely off-site. So, with that.
All right, thanks, Dan.
I'll take this too.
So can I get a show of hands again? The number of folks who have downloaded, looked at, or maybe even used the calculator? Okay, a little more than I thought when we first did our introduction earlier today. So what I'm going to do here, first I'm going to step through the basic elements of the calculator, talking about 2 of the screens where information is entered, results are reported, talk a little bit about how those calculations occur. I'll go through that once, and then I'm going to go through similar material, but specific to the residential development slide that Dan had up on the screen a little while ago. And then after getting through that, you'll see on the agenda there's a second presentation related to the calculator. But instead of that, what I'm going to do, we have it loaded on this computer, and we can do some interactive demonstration of the calculator itself. Okay, terrific. So, okay, so I already talked about the outline of today's presentation, what we're going to do. I'd like to mention the purpose, and this is both for folks who have looked at it and folks who haven't yet. The way I see it, the calculator is a tool that helps, one, achieving compliance easier and more straightforward. It's a tool that should help communication between development engineers and plan reviewers. So the assumptions and results are clearly explained. It manages, I'll put up here, or can be used to address Tier 2 and Tier 3 projects, those that provide water quality treatment and those that require retention. And then also, this last part is what I'd like to talk about toward the end of the presentation more. After setting up DMAs, stormwater controls, it's really easy to change some of the assumptions about the way the site drains, the surface materials, the connection between certain portions of the property and stormwater controls, so that it's straightforward to play these sort of what-if scenarios. What if I take a portion of the site and move it over, move its drainage to another location? How does that affect my bioretention sizing? And that becomes important. Going back to Dan's example about how 4% is pretty ideal, 7% or more can be difficult to accomplish. These what-if scenarios can help the designer determine a more efficient way to accomplish drainage and compliance with the PCRs. Okay. So a little bit on the calculator itself. It's built in Microsoft Excel. Yes?
I'm sorry. You mentioned this 4 and 7%. I guess that question.
Here, can I give that to you?
I'm not familiar enough to understand what the 4 and 7% you're talking about. Can you expand on that and clarify what that is?
Sure. Sometimes you'll see people refer to sizing factors also with bioretention basins. So when we talk about 4%, 7%, or whatever percent, it's the ratio of the plan area of the bioretention basin. It's the ratio of that to the amount of impervious area draining to it. Footprint. exactly. So for a 4% ratio would be 25 parts parking lot, say, for every 1 part bioretention plant area footprint. Does that address your question? Okay, terrific. Okay, so back to the calculator itself. Put together in Microsoft Excel, there's some nice things and some drawbacks to working in Excel. The nice things about working in Excel, built-in calculations. It's an environment, a format people are used to. It's nice for putting together tables and so forth. Drawbacks, and then the programming language in behind is pretty simple too. Drawbacks of Excel is when they're embedded calculations, it's pretty easy for folks to go in and boop, delete the wrong cell, and then calculations don't work, right? And what could be even worse is the calculations not working without making it clear that they're not working. That's even worse. So what we tried to do here, we have a few things. One, the worksheets are protected so that only the cells that require data entry are available. I'll demonstrate this during toward the end of the presentation, but only the cells that are intended for data entry are active. The others are protected. We try to use drop-down lists, combination boxes wherever possible to constrain inputs to acceptable values that the calculations in the background will recognize. One really important thing, right up here at the top, when we open our Excel workbooks, that shows up just below the ribbon. Make sure to enable the macros, otherwise the code in the background won't work. It's not coming across on the screen here, but we try to use some color coding also in the data entry and reporting, so that yellow refers to information that we enter, blue refers to calculations provided by the calculator, and gray are for cells that are disabled based on other sorts of input. Okay. So I mentioned here there are a couple. I should say there are 4 tabs in the workbook. I'm going to talk about the first 2. The second 2 are really background sort of information that we can cover in the demo. Okay. So the first tab, and the one where people will be spending almost all their time, is this project information worksheet. It has 6 blocks in it, 6 different table areas, and I'm hoping that the text is legible on at least one of the nearby monitors. This upper area here is where we enter general information about the project, where it's located, its address, what level of regulatory control, Tier 2 or Tier 3, is required, the 85th or 95th percentile design storm depth for that site that you've looked up separately, and then information here that this total project area, new impervious, replaced impervious, and pervious landscapes. These are things that you would enter directly from your engineering plans. Now the question would be, well, why do I need this information here? Really, only that rainfall depth is going to be used in the calculations. And the answer is, why do we want to provide it, is because this thing is made to be printed at the end and supplied as part of the stormwater control plan. So again, we want to have consistency between what's on this sheet and other elements of the submittal. Okay. The second block in here is the DMA characterization. I'm going to go through that one in another slide where we're zoomed in a little bit better and the information's easier to read. Down below is the SCM characterization, the characterization of your bioretention basins. Moving downward on the worksheet, the next block is a button to launch the code in the background. It's put together to run the Santa Barbara Urban Hydrograph, which I think is specifically mentioned in the PCRs as a technical tool. So there's SBUH calculations in the background. We have a button here so that the calculations don't get updated every time something gets changed in DMA or SEM. So it's an intentional thing. I should say too that if DMAs or SEMs are updated, a little bit of text will appear here next to the results saying the results are out of date. So you can, if you think you're done, you print it, and and it says at the bottom the results are out of date, then you should have launched the model one more time. Okay. So then these next two blocks are the places where bioretention sizing requirements, total minimum storage requirements, depth of gravel beneath the underdrain, and then also time to drain out are reported. And then in the last block at the bottom, for projects that utilize self-retaining areas, that's where the self-retaining areas themselves are listed, the DMAs that drain to them are listed, and then the ratio of the areas. Dan had mentioned that 2 parts impervious can drain to 1 part self-retaining area. If the calculated ratio is greater than 2 to 1, it'll be flagged, the cell will turn red. And if the ratio, of course, is less than 1, then that's reported as well. Okay, so I'm going to step through here. DMA characterization. Here under the name, use the same names you have on your engineering plans, right? Aim for consistency as much as possible. DMA type, this is a drop-down list, and Dan had mentioned the 4 of these in his presentation. We can drain it to an SEM. We can drain it to a self-retaining area. The DMA itself could be a self-retaining area, graded appropriately, or it could be a self-treating, more of a natural area. Plan area for the DMA, its surface type, and the surface type, of course, is important because the surface type determines how much runoff occurs from that area. Whether it's new or replaced, there is accrediting for replaced impervious areas, and then its connection, where it goes. Should say that this is certainly going to be a question when people start using it. This is a dynamically generated drop-down list, and it looks for the available sets of SCMs. So as you go through the worksheet, if you haven't entered SCMs yet, these will be blank, and you'll have to enter your SCMs, come back and make the connection. Okay. So next, going through SCMs again, use names that are consistent, drop-down list to say its type, soils for the property, and the soils for the property will automatically generate an infiltration rate, and then an area for the SEM itself. And then up in the top right, because it didn't fit, we have a new option that's going to be part of the next release, where you can specify whether there will be a flow control orifice associated with the bioretention basin, and if so, what is the depth or the volume in that surface storage reservoir. The surface storage reservoir, it doesn't count, right? Unless, just like the soil volume doesn't count unless there's a flow control orifice. Okay. So I've talked about these 2 already, or these 3. This would maybe be a little more effective to talk about during a live demo. This is that second worksheet, and the only thing I'd like to say about this, so these are the SBUH model calculations. The only thing I'd like to say here is these yellow cells are populated by calculations that come off of that project information worksheet. It gets supplied into these set of Excel calculations at the underneath here. Over on this side, we have results. It calculates the maximum water stored during a storm event, and that maximum water stored becomes the minimum required volume for the gravel portion of the bioretention. And if you have multiple SCMs or multiple bioretentions on a project site, the code generates an SBUH model for each one of those and routes the appropriate runoff to each one. Okay, so let's get through the example and then have a little bit of time to show the calculator itself. Okay, so repeat what Dan had said here. Drain the back portions of the roofs to the yard, drain the front to the front, and the streets would drain toward bioretentions at the end of the block. Okay, now zoom in here. This is one of the lots. The point I'd like to make on this slide has to do with the level of detail to go into when describing DMAs. You know, it's a 9-unit development with streets, so you could say, well, why don't I have, you know, 10 different DMAs, say one for each lot, and then one for the street. And what I would say is that makes the data entry shorter, of course, right? It's not as much information to enter, but it reduces the ability to describe how that drainage is going to be managed. So what I'd say we should aim for is break those DMAs down to the level of detail where you would intend to be managing stormwater. So, and I love this example. I love the roof split in two, because I think that makes so much sense. And it seems if you have a home where down the center is the peak of the roof line, water can drain to the front of the back, it makes perfect sense to me. Maybe you want to manage the entire house the same way, but it would be awfully nice to have the option of managing drainage from that home in two different locations. Similarly, in the front, we have one front yard DMA, a second front yard DMA, and a driveway in between. Those two front yard sections are spatially they're separated, and their grades might be different because of the way that the driveway moves from the street to the house. Again, it makes sense to me that these would be described as separate DMAs, and I think the preparation of the engineering plans really supports this level of this level of detail. So break them down to the level of detail that you intend to manage stormwater to. All right. So after we've done this, each one of these DMAs gets a line in the DMA characterization table. Where it goes, its area, its surface type. Note if it's self-retaining, the surface type is implied. And over here we have our connections. So now the next slide shows we've gone from doing one lot to doing all the lots. So now if this were your project, all DMAs would be defined. So next, okay, SEM setups, two areas are reserved on the property for bioretention basins. And maybe this makes a lot of sense, right? We have maybe an arterial road out here, we have setback, or we have lots that would otherwise be too small to build on. Maybe this makes a lot of sense for stormwater management. One thing to note here when laying this out is make sure that the overall property grading supports the ultimate location of the bioretention basins that water can get there. Okay, so similar to what I just showed on the DMA slide, we have detailed setup here in the SEM table. Have your names match SEM types, soil types, areas, and whether there's a flow control orifice included in the design. And I've said for this example, no. Okay, so after the engineering plans are developed, how long does that take? There are a lot of DMAs. Maybe a couple hours, an hour and a half to enter all that information after the engineering plans are done? Not much. Click the launch the model button and the results pop up. The organization of this is a little funny. 4 and 5 are here, where 6 is up here. It just fits on the screen a little bit better. So you launch the model, and what does it tell us? It gives us a depth of water below the under drain. It gives us a drain time. It gives us a minimum storage requirement for each of those bioretention areas. And it also tells us for the many self-retaining areas included on the project site. I should have noted, actually. Let's skip back for a sec. That each one of these yard DMAs is specified as a self-retaining area, so it would be graded in a concave fashion to accept runoff. So moving forward, so we have our bioretention sizing parameters, and the model also confirms that each one of the self-retaining areas is large enough to meet that 2-to-1 ratio. In most cases, dramatically so. And for those that receive runoff from other areas, the tributary DMAs are listed here. Okay. So we've gone through our first set of calculations. We've sized our bioretention basins. We've confirmed that our self-retaining areas are large enough to control the runoff that's applied to them. The next thing is to say, well, am I happy with the results? I'm thinking about this maybe from the perspective of a design engineer. Am I happy with the results? Are my bioretention basins about the size I would want them to be? Is my, are my gravel depths in the range that I want them to be? And maybe the answer to all those things after going through this once is yes, and you're done. But if you would like to maybe squeeze out one of those bioretention basins, or maybe if the results came back and said you need 6 feet of gravel depth, then we come back and say, well, how can I use this calculator as an iterative design aid where I can play with surface types, I can play with other elements of the design to get my stormwater control measures into the range of sizes that I'm comfortable with. Okay, so examples of things that we could do in this iterative process: reducing imperviousness, modifying our surface types. And I'm going to have a driveway example. Maybe we do the driveways a little bit differently, and then adding a flow control orifice to the bioretention basin. Okay, so coming back to this lot number 1. Well, what are our options? Right now, the plan was to take the back of the house, route it into the backyard, and call that done. We have the front half of the house, 1,800 square feet, draining toward the bioretention basin. Maybe we could drain that to a self-retaining area also. Initially I thought, well, maybe we could put it in the backyard. And I'm kind of glad that I thought that initially, because it raised the question from some folks, or the point from some folks that said, we really want our stormwater management out in front where we can see it as much as possible. So it's fine if you're going to drain the back of the house to the backyard, but how about if we drain the front of the house to the front yard? So let's say we take this 1,800 square foot front of the house, and instead of routing it to bioretention, routed it instead to this 1 FY2. The ratios will work, right? The ratios are a little more than 1 to 1. So that's an option, and it's less water going into bioretention. Here our driveway, I'm going to assume that the driveway slopes down to the street, but if it's not too steep, maybe we can build it, unit pavers, placed in sand. Maybe it could be made out of porous concrete, something to reduce imperviousness. So here, what are the effects of these different ideas? The first one, with regard to the front half of the house, well, we're removing that impervious area from the bioretention. So that's going to have an effect on the bioretention size. Similarly, if we were to take the driveway and put it, instead of having it be concrete, had it constructed of unit pavers, well, then we cut our runoff factor by a factor of 5, which again would reduce the volume of water going into the bioretention. I didn't mention this in the last slide, but another option, depending on the relative grades of the driveway and the property, would be to slide runoff from the driveway over into one of those self-retaining areas in the front yard. Now, one point I want to make is I'm talking about the calculator as a design aid, and I see it as one tool that maybe helps supplement the engineering design process, and it doesn't in any way replace what would be a series of good ideas for engineering design. So, for example, maybe homeowners don't want an emphasis on self-retaining areas in their yards. Maybe there's a concern that we're going to end up with more soggy yards. So maybe it works for the PCRs, but it might not be attractive from from a development and homeowner perspective. So that's my point, is the calculator, it's a design aid, but it's there to supplement, not replace other elements of engineering judgment. Other idea here has to do with adding a flow control orifice to the bioretention itself. Dan, I thought, did a really nice job with the slide that shows the installation of the overflow catch basin. There's a cost associated and an extra design complexity associated with adding the flow control orifice, which means in some instances it might not make a lot of sense, particularly if we're not space constrained. But if we are, then it's a way to really reduce the amount of materials or reduce the size of the bioretention itself. And I guess it doesn't exactly show it here on the screen, but I'd like to describe a little bit why this would work. As our runoff is coming into the bioretention, filtering through the soils and filtering through the gravel, without the benefit of that flow control orifice, as water builds up into the gravel layer and reaches the height of that underdrain, it's gone, right? Goes through the perforations in the pipe and it's out. If we restrict that outflow, what we're doing is we're holding water in the bioretention longer, maybe backing water all the way up through the soils into that surface reservoir. So our outflow is occurring, but it's occurring at a slower rate. Our infiltration out the gravel into the surrounding soils is still occurring. And we're assuming that it's occurring at the same rate. Really, if you build it up, it probably occurs a little bit faster because the water is getting pushed into the soils faster. So by restricting outflows through the underdrain, we're giving an opportunity for the infiltration to catch up. We're changing that ratio. If the bioretention were designed at the same size with a flow control orifice, it would infiltrate more water. But if we're aiming for the same performance, what we can do is reduce the dimensions of the bioretention. Like Dan said, 20%, often more than 20%. Okay. A quick example here that I generated through the calculator. I added 2 DMAs, each with 10,000 square feet of impervious, added 2 SEMs, 2 bioretention basins, one with an orifice and one without. The bioretention without the orifice resulted in a gravel depth of 4.65 feet. The same situation, but a bioretention with a flow control orifice, we're down to a little more than 3 feet. Now, if gravel depth is not the big driver, if it's space for bioretention, then this example, instead of showing a reduction in gravel depth, maybe what you would do is you'd say, well, I want that bioretention with the flow control orifice to be smaller. So instead of, you could have a separate example. Instead of having 800 square feet and 800 square feet, maybe have 800 square feet and 600 square feet, something like that. Okay. So I'm going to move over here. I hope I don't get any feedback. Come out of the presentation mode. Open up the calculator. And before I do anything here, I want to ask, do folks have any questions before we get into specifics on the calculator itself?
Well, you might actually answer this when you get into the calculator, but I think I saw that the bioretention with the orifice had a less drain time than the other one, and they were both the same size.
True. Yeah. Oh, yeah, thanks. So the drain time is the amount of time it takes to get water out of the gravel portion of the system at the end of the storm. Thinner gravel section drains out faster. So if we had a quarter inch per hour of drainage out the bottom, if we're only draining out 3 feet instead of 4.5 feet, it would take less time.
And I think that's for the 95th percentile storm, right?
That one was, yeah.
Okay, so the facility with the orifice actually retains less water in that situation, and it retains more water in the bigger storms, because one without the orifice, the 95th percentile is kind of a maximum, but the one with the orifice will actually retain water in the reservoir above during a larger storm, which would otherwise just be passed out, and those two things balance each other. So you're actually infiltrating less water in this example condition that's shown, and that's in exchange for having a longer drain time from a large, and more infiltration during a larger storm. And the two balance out.
I know there were some other hands up, but I want to make sure that Tony gets a chance to go through, show the Excel spreadsheet before we address the additional questions.
Thank you. All right. So what I'd like to do first is just to scroll through the spreadsheet here to show, say, the project information section, DMA characterization section, SEMs, launch the model, and here are our results. We have the project information tab. We have the SBUH model tab. Say we have 2 instances of the model. The way the code works in the background is it looks to see how many of the stormwater control measures are active, how many active bioretention basins there are, and copies a code block off to the right to make that happen. One other thing I wanted to note, all right, how do I close full screen? Okay, I want to show the ribbon here. Review, unprotected sheet is here. That means the sheet is protected. If we take a look up at the ribbon here, most of these icons are grayed out and unavailable. If I try to delete something outside of one of our data entry tabs, I get an error. However, if I go in here, I don't. Okay. The point I made before about trying to constrain data input to preserve calculations. Okay, so then one other thing I wanted to mention before going through the design iteration example. If you want to look in the background, go ahead and unprotect the sheet. That's okay. There's no password protection on this. If you want to take a look at the code underneath, I should explain it as I'm doing it. Go to any one of these tabs here on the bottom, right-click, View Code, and it brings up the different elements of the code that runs in the background. Okay. Again, that's not hidden and it's not password protected. Okay, so if we go back to this, I'd said, well, what about if we take the driveway and make it unit pavers placed in sand? Before we do that, let's keep these numbers in mind. Bioretention 1, we're saying 2.26 feet below the ender drain. Here's our driveway on lot number 1. Instead of having it be concrete or asphalt, change it to unit paver set in sand, come back down here, launch the model. Our value drops to 1.94. Okay. Let's move that back to concrete or asphalt. Similarly, if we take let's take the front part of the roof, and instead of having it be, actually, hang on a sec. Let's take the front half of the roof, and instead of having that be, bear with me, instead of having it drain to the bioretention basin, let's take the front of the roof. We're going to say we're going to drain it to a self-retaining area, and we're going to drain it to front of the yard. Okay? Again, comparing this to 2.26 down to 1.19 or 1.99. All right. However, the front of the yard, DMA 1 FY1, is only 780 square feet. Our ratio of contributing impervious to the size of the self-retaining area is too big. Instead, and note, color-coded, right? Ratio is too large. Instead, let's drain it to the other part of the front yard. There we go. We're okay. All right? And how long does that take? Once everything is set up, it's quick, right? Very quick and easy to play a lot of what-if sorts of scenarios. And in some cases, it will make sense to absolutely minimize the size of the stormwater control measures. In other cases, maybe it makes sense for them to be a little bit larger based on, say, landscaping goals for a project site or space availability. But regardless, this is a tool that helps provide context and allow the user, I guess, to figure out what the consequences are of different options. Are there other things?
The retention volume. Show them how in the on the SBUH one, the retention volume is.
Oh yeah. Okay, great. That's right. I had this up as a slide before. Our yellow cells are reported from the project information tab. We have a SES type 1 storm distribution here. Gets multiplied by the design storm depth to give us a rainfall. Here we have runoff rates for each here from different surface types. Maybe it's easier to focus in here where we have instantaneous runoff and then routed according to the SBUH calculations. Over here we have inflow to our bioretention. We have direct rainfall on our bioretention. We have exfiltration, so water infiltrating out the bottom into the surrounding soils. And then for each 10-minute time step, we have the retained water volume. So we'll see as the storm goes on, and I hope that these values are a little bit readable on the screen. The volume of water increases, 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 increases. And then we'll hit a peak right around here. That's our peak. Stored water, if we go up to this cell here, it looks for the maximum stored water during the course of the simulation, and that's what's reported here. And then this value, 2066, gets brought back. Into here, 2066. So that's the relationship between on our project information tab, we're setting up all the aspects of the site that generate stormwater runoff and manages stormwater runoff. Calculations occur here in this SBUH tab, and the results get reported back here. Okay. All right, so maybe now would be time for, if there are any other questions about how this works.
So in your calculation, it shows the infiltration rate of the detention pond, right? How about if you have a percolation test on the bottom of the pond, like 2 inches per hour? So how are you going to add that one to the calculation?
That's a great question. Whoops, I'll take this back. Thank you. So, good question. And the Stormwater Technical Guide, I think, has information about site-specific, is this still on? Okay. Site-specific soil tests. Now, if we go back, actually, we can see it from here. If we look at the SCM characterization tab, where it says SCM soil type, there are 3 options in there. There's group AB, group CD, and then there's site-specific. So if you had soil tests, you could select site-specific, and then in the next column over, the infiltration rate, instead of automatically being populated with 0.25 or 0.75, there's an opportunity to provide your own site-specific rate. Now, Dan, if I understand correctly, there are some limitations to infiltration rates that people can claim for particular project sites. Is that correct?
And this is something at the municipal reviewer's discretion. We wanted to set things up so there was sort of an easy way to do it, that you simply specify your soil type and it goes to a default number. We did negotiate with the water board. I guess I would call it a negotiation, that for CD soils, you still use 0.25 inches per hour. And that we actually had some evidence for that based on some work we did in Contra Costa. And I don't think there's any particular limit. If you have 4 inches per hour, you could show it. The question is being able to convince that that's a sustainable long-term rate based on infiltration rate testing. The problem with infiltration rate testing, for those who are familiar with it, is that it's very hard to get consistent results, and it's also very hard to predict what's going to happen over time. So,
it reminds me of a design project I was involved with pretty early in my career, where the site, the hydrogeologists and geotechs came out and did their tests, and it said 10 inches per hour, and then they said, all right, but we're going to put a safety factor of 5 on that. And then at the very end of the report, they said, and we're also going to apply another safety factor of 2. So a measurement of 10 got reduced to 1 by the time we went into our design. Are there other questions? Do you want to do a wrap?
One more.
Okay.
What is the maximum hours we can retain the water in a pond?
So I have a couple different things to say on this. Dan had mentioned one of the benefits of the bioretention, because it's subsurface storage, doesn't carry the same mosquito concerns that detention ponds would carry. In the PCRs and also within the calculator, if the calculated drain time is more than 48 hours or 48 hours or more, I'm not sure, the volume is, the minimum required volume is increased by 20%. So there is an incentive to plan out devices that can be drained within a couple of days. And if there's a question, you say, well, why do we need this additional 20% buffer if the design takes more than, or if the device takes more than 48 hours to drain? And that, I think, has to do with readiness for the next storm. So we want to make sure that these devices aren't commonly wet when the next storm comes around.
Great. Thank you so much, Tony and Dan, for the presentation. Silvio, thank you for taping this. That concludes this today's training. So, thank you very much for attending.